This is question 1 and we're going to solve this question now. So today we will solve 2 more problems from this chapter, and I believe it will give you a very clear understanding. So if you can understand this problem, then you can solve any problem from this chapter. So you need to understand the basics, and there are a lot of things that we need to consider. So let's say a jet of water impinges on a vane tangentially. So this is the area of the jet. The initial velocity is vi and this is the area ai. So this is the water jet. Okay, the vane is here and the jet of water impinges on the vane tangentially and then it deflects horizontally and it creates a a 60-degree angle here with the horizontal axis. So this is important. We already know we solved many problems. The force or the pressure, we calculated the pressure or force for a curved surface. When it is curved, you can remember we need to consider the pressure or the force component along x or y axis, especially because when the direction changes, you need to consider every directions. Anyways, the vane itself is moving with absolute velocity, which is 4 meters per second. So this is the vane absolute velocity in the same direction as the incoming fluid. So the fluid is coming this way, so this is the same direction. Let's say this is our coordinate system. So this is the positive x directions and this is the y directions. So this is our coordinate system. The jet absolute velocity is v1 vi. This is 22. This is the inlet velocity and the corresponding area is 0.01. Assume this is a frictionless flow. We need to determine the magnitude and the direction, that means the angle of the force, by the water on the fluid. So this is really important. These two terms, by the water on the moving vane. So definitely we're going to discuss, and the power generated by the vane. So if I start solving this problem, so 2 important keywords here. You can see the absolute velocity. The absolute velocity. What is the absolute velocity? The definition is given here. The absolute velocity is the velocity with respect to a stationary observer. So let's say you are sitting on a bench inside a park and you can see some other people. Maybe he is walking in the south directions and his velocity, he is walking maybe at 10 meters per second. That's the velocity. So that 10 meters per second, this is the absolute velocity. Now we have decided, okay, you will start walking. So you have started, your velocity is maybe 4 meters per second. So then that means you are going similarly to the south directions. Okay, so both are in the same directions. That means the difference between your velocity and the other people's velocity, this is called the relative velocity. So the relative velocity is something which is the velocity difference or the velocity with respect to a moving objects, where the absolute velocity is with respect to stationary objects. So now in this case you can see the vane it is moving, right, with an absolute velocity 4, and in this case jet absolute velocity is 22. So both are moving. So vane is moving this way, the water jet, the flow is going this way. So this is another inlet velocity. So we need to calculate the relative velocity. So let's calculate the relative velocity at first. Right. So what I said, let's put this diagram here. This is the inlet, this is the exit or outlet. So what we said is maybe at the inlet and the outlet it has the gas pressure, so that means the zero pressure. This is the vane, this is the the velocity u, the direction, it creates the 90-degree angle here. The inlet velocity, we say this is wi. Okay, So velocity, we are using this notation Wi, and definitely then for outlet it should be Wo. Okay, and the vane, its velocity is 4 meter per second. So this is the absolute velocity. So with the moving vane, the relative velocity of the vane is, this is jet velocity 22 minus 4, that means the 18. So we calculated the relative velocity, and I said earlier relative velocity is something which is, you need to calculate with something moving, and the absolute velocity is with respect to some stationary objects. So according to the the Bernoulli principle, we know energy conservation principle, equation of continuity. So according to the the equation of continuity, the mass flow at the inlet and the exit, it should be equal. So that's we know from our previous understanding. So the mass flow at the inlet and the outlet, it should be same. We are going to calculate. We are going to apply the Bernoulli equations at the inlet and the exit of this system. So you know the Bernoulli principle. This is the pressure at the inlet over rho g, the velocity squared over 2g, and the elevation at the inlet, and the pressure at the outlet rho g, the outlet velocity square, and 2g, and the z elevation. That means the elevation at the outlet. We said our assumption is okay. We have the gas pressure at the inlet and the outlet, so that means we can put this term is 0 because this is the gas pressure. So if it is 0, then it should 0 over rho, that means 0. We are considering the elevation difference. This is same at the inlet and the outlet. So that means then we have the W, that means the velocity at the inlet squared over 2g is the velocity at the outlet squared over 2g. So you can eliminate this 2g, and this is square. So it will give you like the W in, W out. This is equal. And that's actually we calculated the Wi equal 18. So we can say, okay, that's the maybe the velocity at W in and the W out. So we got it from the the Bernoulli equations. We applied Bernoulli equations at this inlet and this outlet. So now we found that W in, W out, this is 18. So once we know this, so you can see our ultimate target is to calculate the magnitude, the velocity magnitude, and the directions. We actually want to calculate the force. Okay, if you see, if we consider the control wheel moving with the vane, so see here, this is the Wi, this is W naught, right? The area is AI here, this is inlet, A naught per outlet. If you can remember, it creates a 60-degree angle. So it was the vane, okay, so it was the vane, moving vane, so it deflects here, it creates a 60-degree angle here. So if it creates a 60-degree angle, let's draw this one. So this is the horizontal axis, x-axis. It creates a 60-degree angle, and this is the W naught. You see, this is W naught, the outlet velocity, and this is our y directions. So during the class I discussed actually the velocity component along the x-axis. This is W naught into the angle. This is for horizontal axis, this is cos. For the vertical axis, this is sine. So when it is the horizontal axis, you say this is the horizontal axis x, this is x, this is our y. So it should be W naught cos 60, it should be W naught sine 60. So that means the velocity component for outlet, due to this angle, it's changing the direction, so we have two velocity components along the x and the y. Similarly, you see, according to the Newton's third law of motion, every action has an equal and opposite reactions. So the fluid, the water that it is, putting some force on the vane will create some opposite force. So initially the fx, it was, the This is the positive directions, but the vane, it will create some opposite force like this way. This is Fx, and the other force Fy like this way. So that's the two things happening here. So this is the force by vane on fluid. If you see the problem here, we need to calculate the force F by the water on the moving vane. Okay, and the magnitude we need to calculate the magnitude, and for directions theta, that means the angle of force by the water on the moving vane. Okay, then we'll calculate that on later. So you know from the momentum principle we discussed during the class, this is the final term. The sum of the force, the wall forces, it is equal to the moment. The F equal, this is the rate of change of moment, sum of the rate of change of the moment. So this is B, the rho B dot A. So you can write it like different ways. So what we need to do is we need, as we can see here some change of directions, so we need to calculate the force along the x-axis and the y-axis as well. So along x-axis, the net force Fx, you can see we said we have gas pressure here, so that means that P1, we have the gas pressure P1, it is equal to 0, and we know the area. So as the pressure is 0 here, so that should be 0 pressure force along the x-axis. Similarly for the y, this is also the gas pressure is 0, so there should be 0 pressure force along the x-axis. Okay, so for the outlet, and for x-axis we have only this force Fx, and you can see it is going to the opposite directions. So that's why you can say this is negative here, negative Fx. So that's the net force we have. Now for the net momentum. So the formula is sum of V rho P dot A. So we can write the rho here, and we are calculating along the x-axis. So we wrote it is Vx, and this is the dot product B dot A. This is the formula. So you can see your lecture notes. And if you attended the tutorials, then you can clearly see we explained everything. So if you can go through the books, then you can see all the derivations. Anyway, so we can put the rho here, it doesn't matter. So this is sum of Vx dot V and A. So we need to calculate the rate of change of the momentum. So what I want to tell you now, in different books, people use this problem different ways. People usually explain this by using different, they follow different styles. So I actually want to make this problem very simple to you. So what I want to tell you is you need to calculate the rate of change of the momentum. See, I said the outlet momentum, you need to write the outlet momentum at first and then minus the inlet momentum. So this is our outlet. So we will calculate the outlet momentum at first, then we will subtract the inlet momentum. So what is the velocity? So that means according to this formula, outlet moment. So what is the outlet moment along x-axis? The velocity Vx. You can see due to this 60-degree angle, we have the velocity along x-axis is W0 cos 60. So we wrote W0 cos 60. And this is the velocity along x-axis, and the V is actually the velocity, normal velocity, W0. This is not W0 cos 60. It is only the W0. So you need to think that, okay, this is only the velocity component along the x-axis, and this is the V0, and area is A0. So this is the final moment or the outlet moment. You notice the initial moment, then once you know the final moment, subtract. Now go to the initial moment. What is the velocity Vx at the inlet? This is wi, no cos theta or sin theta, because you see there is the angle is 0 here. This is at this inlet section, it is not creating any angle. Like at outline it was creating 60-degree angle, but no angle here, so 0-degree angle. So you don't need to think about that. You can only see the velocity is wi. So this is wi and dot wi ai. So this is the initial inlet moment or the initial moment. So there's the difference of the final moment and the initial moment. So when we will solve any problem in this chapter, we will calculate the final moment at first, we will subtract the initial moment. So you will see some other example later. So now you can see we know the value of W naught, we know the A naught and the AI. So let's calculate the WI and AI. So WI is we got 18 and the AI is given this. So WI AI equal 0.018. So as the WI and the W naught is same and the area is same, so that means the WI AI equal W naught A naught. So if these are same, like we got 0.018. So now substitute the values here. The rate density is 1000. W naught equal 18 cos 60. This is W naught A naught 0.018. Similarly, W equal 18 and this. So we got a force is negative 162. This is the moment, sorry, this is the net moment, negative 162. So now go to this momentum principle. Sum of x equals sum of this. So the net force is negative fx. So we can say, okay, this negative fx equal negative 162 Newton. So you can eliminate these two terms and the fx is 162 Newton. So that means this is the force along x-axis on the fluid. So this is positive, means this force's direction is like this way. If you see here, this is the fx we calculated. So this fx, we calculated this force fx. Yeah, you see here this fx. So we calculated this fx, see this direction, as it is showing the positive, so that means this is this way, and this is the force along x-axis on the fluid by the vane. So that means there should be an equal force on the vane by the fluid. So force on the vane fx equal 162, but that direction it should be opposite directions. So this is very important. What I said, this force, it is the force along the x-axis on the fluid by the vane. So this is the directions. So once we calculate the force on the vane, see force on the vane, it should be the opposite directions. We got the fx. Now we need to calculate fy. So now along y directions. So along y directions, the force fy on fluid, it is, we said it is equal to the density gravity of Vy and V dot A. So you can see from this figure how many forces we have. Do we have any force along, so this is inlet, do we have any force along y direction here? No. We have the Fy force here, right? Do we have any force here along y direction? No. So that means the only force is Fy, and this is the positive directions. So you can see this is Fy, and it should be equal to the moment along the y directions. So now same like what we did for the first problem, we dot rho here and Vy v dot A. So similarly the final moment minus the initial moment. So look, we have no mass along the y direction, definitely no moment. We have no mass here along these directions, so no moment, but we have only okay, so two things. Dude, it creates a 60-degree angle here, so we have this is the y direction, so we have this velocity w0 sine 60. So definitely we have the moment here. So this is the w0 sine 60 along the y directions, and the, you know, I said previously, when it is, this is it could be vx or vy, so you need to only change this, and it would be w0 a0. So, and the final moment, we have no velocity, no mass this direction, this is 0, so we will have 0 for this part. So now you see Fy equal, we know rho equal 1000, this is 18 w0, and we know all this value, this is 18 and 0.001, so we got this is 281. So this is the force on fluid. Okay, so force on fluid, this is 281 Newton, and the direction is this positive directions. So that means the force on vane, this is force on fluid, so force on vane along y-axis is, it should be an equal amount of force 281, but it should be the opposite directions, because this is, you know, the Newton's third law of motion. So when it is the force on fluid is upward directions, so there should be some opposite force, like force on vane along the y-axis, this is the negative directions. Right, so we calculated the Fy and we already know Fx on 62. Now we need to calculate the resultant force. So the resultant force, the formula is, you know, Fx square, square root of Fx square, Fy square. So this is 162, this is 281, so we got 328. So this is easy, we got the magnitude. Now the directions. This is a little bit complicated, because you guys will do some mistake with this. So the direction means we need to calculate the angle theta. The general formula we know, the tan theta equal, you know, the vertical Fy force Fy over Fx. So that means theta equal tan inverse Fy Fx. You need to be careful actually. You see, when we calculated the Fx, so you see the Fx, the force along x-axis on the fluid. So the force on the vane, that should be the opposite direction. So when we'll calculate, you see the Fx is in the opposite directions, 162. Look at this arrow here. Previously we got Fx, it is this directions. So now we're calculating the angle. We said okay, Fx is this. Fy, it was the positive direction. You see, we said Fy is the negative. This is actually the force, force on the vane along y-axis. Okay, force on the vane. So you see, we have this force along this direction, and this is the force, the resultant force. So now, why we're taking that? You see, we need to calculate the angle of the force by the water on the moving vane. So that's the important thing. So now if I go back there, so you can see we said okay, this is the Fx, this is the Fy. It creates the angle, like this is the theta, this is the force. It creates the angle theta here. So now if you're confused why it creates this angle like here, why not this angle? So let's see your diagram, the figure you have. So look here how it creates this angle. For the moving vane, this is the force acting this way, so it should be the Fx force and it should be the Fy force. You see, it creates this angle here. So this is actually theta, so that means this is our horizontal axis. So now you go here. So you see, we said the general formula is this is Fy over Fx, but it is, you need to always consider okay, it creates the angle this way, so it should be this force over this force. So that's why it's 162 over 281. If it creates the angle like let me just remove this one. If it creates the angle theta here, then you will write okay, this force over this force. So that's the important thing. So you see it creates a 30-degree angle here. So that's it. So you need to keep in mind this information actually. So this is very important, and when you are calculating the angle, so you need to make sure that you have the exact force, your force direction is accurate. So that's it, and now we'll start other problem.